Alright, welcome to the second video in the VHDL tutorial series. This video's main focus is going to be all about combinational logic. So if you remember last time, we talked about in the architecture the declaration section of the architecture command. So this is going to go over signals. Signals are basically intermediate variables for like a function or whatever. So if you're writing up like say a full adder, here, sum 1 and carry 1 are essentially, the Boolean expression for a full adder. So, we have here A1 XORed with B1, all of it XORed with C1, and then here we have A1 and B1 ORed with A1 XORed with B also ANDed with C1. That's a mess. That's a complete and utter mess. So signals, though in sequential logic they're used for something different, in this case we're going to be using them as sort of like intermediate variables. So you see here that, S1 is A2 XORed with B2. That's the exact same thing as this expression up here. S2 is A2 and B2, which is the same thing as here. And then S3 is C2 ANDed with S1, which is, that's going to be representing, this whole block right here, because S1 is A2 XORed with, I wish these things wouldn't appear, A2 XORed with B2, and then ANDed with C2, which is the exact same thing as this highlighted block of code. And then after doing that, we can just do sum2 is, S1 XORed with C2, and S3 is, or carry 2 is S3 ORed with S2. And these produce the exact same result. More into detail about the signal declaration, you would first type up, signal, right? And then you can, we have 3 signals, so I just named it S1, S2, S3. And then you do not need a mode because it's an intermediate variable. It's essentially fake, because when you compile it, all it's doing, or not compile, when you synthesize it, it's not compiling. When you synthesize it to like a PLD or an FPGA, it gets rid of all of the abstraction and it just interprets it as pure combinational logic. So you don't need a mode at all, but you do need a type, and the type is going to be STD logic. So let's run a quick simulation of this. All right, here's the simulation. I've already set it up, so let's click play. We know the full adder, here's A1 and A2. They're tied to the same input, and then sum 1 and 2. As you see here, they give the exact same outputs every single time. The next fundamental combinational logic concept is the when statement. So here we have, basically this is a 7-segment decoder. So what we have going on here is that we have an input, we have the 4 inputs and then the 7 outputs. This is like a 7447 essentially. So all's good and well. We assign seg using the less than equal to sign, but here we have, segs is, this, which represents a 0 in the 7th segment, when q is equal to 0, 0, 0, 0. Else represents a 1 when q equals 0, 0, 0, 1. And then it repeats and repeats and repeats and repeats until you have, 15. Else it's going to just equal 0, because otherwise we don't have anything. And then here with the when statement, you can have like as much stuff as you want. You can have, when q equals that, and, or, XOR like h is less than like 111. That's a completely legal statement. So, yeah. And you see here how this actually has the equal sign, because instead of assigning, this is actually a comparison. And I'll just show you right now, even though we're going to learn it later, that the assignment thing. So, of course we have an equal to sign. We have the less than, greater than. I believe this is less than, equal to, greater than, equal to. I'm not sure. And then this is not equal to. In C++, you would be using exclamation mark, equal sign. But here it's just slash equal sign. And then we also have the don't care equal, which we'll get into a little later in this video. But yeah, this is the when statement. And then I'm going to quickly set up the simulation, and then we'll see how this works. All right, so I've set up the simulation. Here's a neat little thing, because since it has vectors on, a single line, you can split the input. So the input, we have 7 bits on a single wire, and then we have 1 bit on, 7 wires. Then we connect it to the display, which we have set to have a common connection, and that is an anode. All right, so let's begin the simulation. Now it's going to start at 0 because we're at 0. We can just go up 1, 2, 3, 4, 5, 6, 7, 8, 9. And because I made it so it actually does hexadecimal, we have an A, a B, C, D, E, F, then all the way back to 0. So that's the simulation for the when example. And then next we're going to move on to the select statement. Okay, so right here we have the select statement. It is essentially the exact same concept as the when statement. However, down here, we have begin, and then we have with SEL select. And then we have inside of this thing, we have, this is a multiplexer. So the whole concept of this is we have 4 inputs and then 1 output. And then we have a selection. Depending on the selection, it chooses which wire to output. So, if we have it on 0, it will select D0. 1 is, D1, D2, and then D3. So instead of having to write, when SEL equals quotation 1, 1, we just have with SEL select, and then inside of here we have mux out is, it is D3 when SEL is 1, 1, D2 when it is 1, 0, 0, 1, 0, 0, and then 0 when others. So you have to have the when others statement, because sometimes there's unexpected behavior within the chip, and then it's not going to know what to do. So you need to have when others just for like a control statement. So I'll set up the simulation for this, and then, yeah. All right, so here we have the multiplexer. So we have, our 4 inputs, D0, 1, 2, 3, and then we have our selection thing, and we have our output. So in theory, because it's on 0, 0, that means output is going to be whatever this input is. So let's demonstrate this. So, we're playing, put him up, there we go. Let's just have it like here. So it's on 0, so we're accessing D0, and that's currently 1. If we go up, we're on 1, that's a 0. And if I toggle him, on and off, up to 2, and then 3, and then we're back on 0. Yeah. So that is how to basically do. Oh, let me go back here with the with statement. this doesn't just have to be a variable. It can also be like an equation of some sort, you know, with like L is equal to 0 and H is equal to 1, like that sort of thing. All this basically does it has an abstraction from, instead of having to do when Q equals this and blah blah is greater than or equal to like 27 or something, you can write all that here, and then it will, you know, interpret that within the with statement. So yeah, that is it for the with statement. All right, here is an example of a comparator. The role of a comparator is, you know, we have two, you know, input vectors of, you know, it's 8 bits long. Here, this is just another way, a generic, and it's like just a constant, so we can have, you know, n minus 1, which is the same thing as 7. And that's just if you might find that useful if you don't want to type out, you know, like 8,243 or something. You can just have it as a generic n. And yeah, so we have, you know, two 8-bit vectors, and then we have the outputs equal, not equal, less than, equal, greater than, equal is an out standard logic. And then here in the architecture, we have equal is 1 when A is equal to B, else 0. Then here we have it 1 when A not equal to B, else 0, less than, equal, greater than, equal. So yeah, this is a very useful application of the when statement, and it also does the comparative operators. So yeah, this is I'm not gonna simulate this because, you know, it's gonna be what we expect. So yeah. Okay, this one I am going to simulate. This is a example of the do not cares. So right now we have a priority encoder. So you might be wondering, what does this mean? So what happens is that it takes its input, right? And then it has, you know, the output. They're of the same bit length. The the output depends on the highest bit of the input. So when we have, you see here, we have, this is the most significant bit is 1. When the input, the most significant bit here is 1. And then we have 3 dashes here. The 3 dashes are a way of saying we do not care whatsoever what these values are. They can be 1, 1, 1, 0, 0, 0, 1, 0, 0, blah, 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 blah. It's just saying as long as this first bit is 1, then this is going to output that. And then, you know, we have it here. It's a 0, 1. You know, when input question mark equal 0, 1 dash dash. When 0, 0, 1, when question mark equals 0, 0, 1 dash. Then also here, otherwise it's going to be a 0. So let's simulate that. Okay, so we have the circuit all set up. Here's the simulation for it. We've got, let me start it first. So we have nothing, so it's going to be, you know, 0, 0, 0. That's pretty obvious. Then we go down here, and as expected, that would be 0, 0, 1. Let's go all the way up here. Now we have the most significant bit is 1, and everything else is 0. Even though if we play around with these guys down here, nothing's changing. When we change the most significant bit, or the priority bit, we have a change on the output. You know, and that's how we use the do not cares in the Oh my goodness. That's how we use the don't cares in VHDL. So this wraps up essentially what is the very, very basics of combinational logic. Next is going to be sequential logic, and I expect that video to be tremendously long because there is a lot of stuff to cover. I think I might actually split it into two parts where it's just basic sequential logic, and then we're going to have like state machines, and then the different functionalities of that, like converting types and whatnot. So stay tuned for that, and I hope you all found this educational. I know this is extremely unprofessional. I'm not a teacher at all. I'm only like a student. So, yeah. But as long as you're getting something out of this, that's all I care about. So, have a nice day. And leave a like. That'd be nice.